participants in this program. Thank you.
I request Anup to formally introduce Dr. Rajesh.
Both you can introduce now.
Yeah, Dr. Rajesh and Dr. V.S. Prasad.
Thank you so much, sir. Respected DG, sir. Speakers for today's talk, Dr. Rajesh Kumar and Dr. V.S. Prasad, senior colleagues from IMD, and all the participants, both offline and online. A very good afternoon and namaskar to all of you. I'm Dr. Anup Misra from IMD New Delhi, and I'm very pleased to get an opportunity to introduce our speakers to the audience for today's talk. We are honored to have Dr. Rajesh Kumar and Dr. V.S. Prasad. Dr. Rajesh Kumar received his PhD in Earth Sciences from University of Hamburg in Germany. Dr. Rajesh Kumar is interim Deputy Director of Research Application Laboratory, that is RAL, at NCAR, National Center for Atmospheric Research, Colorado, USA. His research primarily focuses on air quality, and it is one of the most important socioeconomic and environmental concerns around the world today. Dr. Rajesh is a recognized expert on a range of air quality topics, including analysis of in situ and satellite products, emission estimates, source attribution, aerosol and dust modeling, chemistry, climate simulation, air quality forecasting, and chemical data. Dr. Rajesh is the recipient of Baron Nicolet Prize by Royal Belgian Academy of Sciences. Our second speaker for today's talk is Dr. V.S. Prasad. Dr. Prasad has obtained his PhD in meteorology and oceanography from Andhra University and carried out postdoctoral studies, that is JSPS fellowship, at Kyoto University, Japan. Presently, he is heading National Center for Medium Range Weather Forecasting, NCMRWF. He played a very crucial role in developing state-of-the-art data assimilation systems and operational ensemble forecasting system in India. Under his leadership, NCMRWF successfully carried out first ever global rain analysis project in India. And Dr. Prasad's main area of research are data processing, satellite data retrieval, and data assimilation. Dr. Prasad published more than 100 scientific research papers in various national and international journals. And he received many awards such as B.N. Desai Medal, N.M. Philip Prize, Mosam Biennial Award, MOES Merit Certificate, GSPS Fellowship, and he is also elected as IMS Fellow. I request all of you to join me in welcoming both the speakers.
Now I would request Dr. Rajesh to please start his presentation too.
Okay. Yeah, you can speak.
Yeah, so first of all, I would like to thank Director General Sir for his nice words and warm welcome to IMD. I would also like to thank Dr. Soni and Dr. Anup for all the arrangements, and also as well as all of you for taking time to come and hear us talk today. So thank you so much for this opportunity to tell you a little bit about our lab, the Research Applications Lab, which is dedicated to expanding the reach of actionable atmospheric sciences. And then I will focus on the Delhi air pollution problem in the second half of my presentation. Next slide, please. As you all know, that climate change is fueling extreme weather and climate events worldwide. Here are just a few pictures. On the top left, you see 2020 August complex fires. And these fires were so strong that smoke from these fires was transported even to Europe, which is like 8,000 kilometers away. Delhi air pollution problem, this is a photo of the recent event when we had one of the worst air pollution episodes in the last 5 years. And unfortunately, I believe all of you had to experience that episode. And I will talk a little bit about that into later half of my presentation. Then you see some other events like the Ida hurricane that trapped Louisiana in August 2021, Rajasthan floods from this year, heat wave in Mumbai, Somalia drought. So these are not place-specific examples. These are actually, these type of events are happening everywhere in the world. And we know that these climate change is mainly attributed to the increases in concentration of greenhouse gases around the world. Next slide, please. But if you look at historical emissions of CO2 and the contribution of different countries to those emissions, then we realize that developed world, which is mainly North America and Europe, they have contributed nearly 80% of the global CO2 emissions. And Africa, which hosts the most least developed nations across the world and is most vulnerable to the impacts of climate change, they are contributing very less. In fact, there is no African country among the top 20 emitters of carbon dioxide. Next slide, please. And then if you look at this climate change vulnerability index, so the climate change vulnerability index is on the y-axis, and then on the x-axis you have average annual percentage change in population. So Europe and Americas, they are in the blue colors, and Asia and Africa, they are in orange and red colors. So on this graph, if you are on the left side, it means you are less vulnerable. And if you are on the right side, it means you are more vulnerable. So can you click one more time, please? So least vulnerable countries in terms of the impacts of climate change, they are the focus of more than 80% of the research studies. And remember that the population change in those countries is very less, as the population change is less than 1%. Whereas if you look at the top right and click one more time, please, you see that the most vulnerable countries are located in Africa and Asia, and only 20% of the research activities are focusing on that region. So a lot of the knowledge about weather and climate sciences lies in the developed world, but developing world is the one that needs this information the most. There is another thing, if you go to the next slide, then you see that we need a one planet, one problem approach to address this issue, because you see that the greenhouse gas, their lifetime ranges from 12 to 50,000 years. And on this map here, you see the atmospheric mixing timescales. So you can see that pollutants can be transported from one continent to another in just 2 weeks. And a carbon dioxide molecule emitted in this room today, it can actually go to Antarctica in 1 year. So if you compare those time scales with the lifetime of greenhouse gases, then it means that we cannot work in silos. We cannot just focus on our own countries, and we need to take an integrated one planet, one problem approach, which means we need international partnerships to accelerate the development of solutions to the weather and climate problems that we are focusing. Click one more time, please. Yeah. So these international partnerships are essential. Next slide, please. And so that's what is the focus of our laboratory at NCAR. We are called the Research Applications Laboratory. We are one of the 7 NCAR laboratories dedicated to expand the reach of actionable atmospheric sciences. We have about 190 people in our group, with a mix of atmospheric and social scientists, physicists, mathematicians, software engineers, administrative staff, etc. And we are 90% soft-funded, which means that even though NCAR is sponsored by the National Science Foundation, 90% of our funding comes from external sponsors, which includes the other government sector of the US government, because we focus on the problems that are faced by different parts of the US as well as different parts of the world. And we do research to solve those problems. So our mission, based on our current strategic plan, is to conduct fundamental and use inspired. So we know we not only focus on solutions, but solutions always lead to better understanding of what are the current gaps in knowledge, and that derives the fundamental sciences done at our lab. And we really want to contribute to advances in understanding of the Earth system. Another component of our mission is to extend the capability of scientific community. Because if we want to have solutions of these problems worldwide, people from the developed world cannot just walk into a country and say, we have a solution to your problem. We need local leaders and local champions to solve that problem. So I strongly believe that the developed world people need to take a backseat role, and they need to support scientists and leaders in the developing nations in developing system to develop the local capacity, so that they can continue those things even after some type of foreign partnerships end. And so transfer of knowledge and technology for the betterment of society is the third key aspect of our lab. Next slide, please. I would like to briefly tell you about why was our lab established. We were established like in late 1970s. And the reason that we were established was there were a lot of plane crashes happening into late 1970s in the US. And we did not understand why that was happening. So the Federal Aviation Administration of the US came to NCAR and said, help us understand this problem. And so if you just look at the orange bars in this graph, then you see year of accident and number of fatalities in different plane crashes. So in 1970s, we had 96 deaths, 1975, 112. So the number kept increasing and increasing as we had more airports and more aeroplanes. The other numbers in the other aspects on this figure, I will explain later. But this was really the start of our lab. At that time, it was called Research Applications Program. And we started with a group of 3 people who were dedicated to understand what was causing these plane accidents. Next slide, please. And so this actually shows why were those aeroplane accidents were happening. So if you look at the figure, the image on the right, you see a microburst happening. And so imagine during those microbursts, the wind speed, the downward wind speed is about 100 miles per hour. And if an airplane comes into that area, then it is pushed into the ground with such a large velocity that there are no survivals. So basically, NCAR, this research application program team, they designed some experiments, and then they came up with the physical understanding of the problem. So basically, what was happening is whenever you have a thunderstorm and when you have an area of dry air, so when the cloud drops are falling into that area of dry air, there is an evaporating cooling of that area, which makes the air much denser and leads to very, very high wind speeds. And generally, these microbursts, these are not very large systems. These are like maybe 1 to 3 kilometers in the horizontal distances, and the wind speeds are like 100 miles per hour. So based on this physical understanding, we designed a solution. Next slide, please. So we call this a low-level wind alert system. It was developed, and so if you see like if you follow the wind barbs, what we do is we put a lot of remote weather measurement stations along the runway of the aircrafts, and then there is a master station which polls every stations every 10 seconds to see what is the wind speed, what is the wind direction, and then they make wind shear calculations based on those measurements. And so if the wind shear calculations detect any type of microburst type of situation, a warning is sent to the pilot, and they are advised to avoid this area of microburst and maybe either go to a different aircraft or wait for that microburst situation to go away. So the Federal Aviation Administration has installed these low-level wind alert systems across the US, and we are also licensing these globally to other airports in the world. This is also installed in Taiwan. We are currently working with Bahamas on installing this system there. Next, please. And so now you see here that this wind shear research and demonstration, it really went from 1970s to 1990. And then by 1980, we had a good understanding of why this is happening. So pilot training was done after that. And then the system was installed along with the terminal Doppler weather radars. And after 1995, we are really pleased to see that there has not been a single death because of an aircraft crash due to these microbursts. Next slide, please. So this aviation was just the start, and our research application program mainly focused on the aviation part till 1994. But after that, we started diversifying into different areas. And right now, as you can see, that we grew from a group of 3 people to a lab of 190 people. And there are a lot of focus areas in our lab right now, which includes agriculture and food, air quality, and I'll spend later half of my talk on air quality, aviation, climate, high impact weather, human health, urban plume dispersion, renewable energy, surface transportation, water is a big focus, and wildfires. Next, please. This is just an organizational chart of our lab. I believe you will have these slides later on, but we are broadly classified into 5 different programs. Our original program is the aviation application program, about which I just talked about. There is a national security and application program where we collaborate with US Army to provide customized numerical weather predictions for all the Army test ranges in the US, as well as we help the Defense Threat Reduction Agency of the US better understand if there is an explosion happen somewhere, if there is a chemical explosion, etc., then how is that going to affect the residents in a particular areas. And our air quality program also sits under the National Security and Application Program. Hydrometeorology application program, this is where we developed the WRF hydro model, which has been adopted by NOAA in the US to as a operational flood forecasting model. The NOAA MP land surface model, which is very popular in WRF, is also developed under the hydrometeorological applications program. And then we also do a lot of climate modeling under that program. Then we have weather systems and assessment program, which focuses more on the renewable energy production using statisticals as well as AI/ML based methods, fire behavior modeling, as well as boundary layer modeling. And then finally, we have a joint numerical test bed, which works closely with NOAA on the development and testing of the NOAA models. Next slide, please. And then we have, you can click multiple times. We have a lot of affinity groups that are across these programs that allows people across these programs to collaborate and work collaboratively on different issues. Next, please. This is very quickly our spending by sponsor categories. So we have a budget of about $30 to $35 million every year, depending on the people that we work with. There is significant funding diversity. We also work internationally. So you can see there that we have about 14% of our funding coming from international sources, including we have also worked with Indian agencies. Next, please. So I'm gonna show some technology highlights from our lab. Next one. So each of these is an animation. So maybe if you go there, you should be able to find a video play button. Yeah. So like this one, if it plays, I don't know if it will play because it was made on a Mac. None of them will play. Oh, anyway. So the top left here was showing kind of a simulation of a hurricane as it approached Florida. And then the next one was showing the simulations of WRF hydro model, how that is used for flood forecasting. The bottom one is WRF fire, which is a fire behavior model and simulates the evolution of a wildfire as it happens in real time. And then the right one was showing the WRF LES dispersion. Next, please. This is one machine learning based S2S drought forecasting system that our group has developed. Basically what it does is it takes the information from pre-summer hydroclimate, and then it forecasts the drought during the summertime. So if you look at the scatter plots on the right side, these are for meteorological droughts and agricultural droughts. And we have the correlation coefficients between our predictions and observations is more than 0.85 in many areas. So this is something that we are trying in prototype mode, and also looking to test the systems in different parts of the world. Next, please. And then we all know that when we produce information, that information cannot be easily understood by the public. So we work on developing powerful and actionable visualization to effectively communicate storm surge risk. Say, for example, there is a video, I do not know if it will play in the next slide, but you can see the image on the left here is how the conditions look like in a neighborhood 5 minutes before the storm surge water makes it to the neighborhood. And so if you provide these type of visualizations to people and saying that, okay, within 5 minutes you will have this much water in your area, that will probably help them make more informed decisions. Next slide, please. And let us see if this video works. Okay, so this one also not work. Anyway. So these are some of the examples of the benefits and impacts. Can you please click? So the low-level wind shear detection, it is estimated to save $5 to $10 billion since it has been implemented at different airports. And these estimates, they have not been made by our lab. These estimates have actually been made by the sponsors who have performed this research. Next, please. Nearly $1 million in a single afternoon saving at the Chicago airport, about $60 million per year for the icing products. Our winter road maintenance decision support system is used in 15 states. And in one of the states named in Indiana, they save about $12 million in one winter. Similarly, Xcel Energy, which is a electricity company that uses our renewable energy prediction systems, they estimated that they save about $60 million because of the accurate forecast. 10 to 30% improvement in hurricane track forecast. NWS, the National Weather Service, has selected WRF Hydro as the national water model. We also did research in vector-borne diseases, and this was highlighted in 840 media outlets, and it also made it to the White House press briefing. And the solar energy predictions with a 50% reduction in error, nearly $450 million accumulated saving over 26 years. So this is just an example of how we are advancing this reach of actionable science in different areas of the world. So this brings me to the second half of my presentation, which is on Delhi air pollution. And I call this as an evolving story of science in service of society. And it is actually an international partnership between IITM, IMD, and RAL. Next slide, please. And we started because of this day, 8 November 2017. It is sometimes called Red Letter Day in the history of Delhi. The air quality index reached 999. Next, please. And so Indian Medical Association declared a public health emergency back then and called the conditions equivalent to smoking 50 cigarettes a day. Kejriwal ji called Delhi a gas chamber at the time. Maximum PM 2.5 concentration on this day. This is instantaneous value. Is reported to reach 1500 micrograms per meter cube. And then you can see that a person on average loses 6.5 years of their life due to exposure to air pollution in Delhi. But so I think the government has been really proactive. I know that government is really criticized a lot for not managing this episode, but I would like to take a minute and highlight various initiatives that the government has taken to address this problem. When we started in 2017, we only had about 20 stations. Now we have about 50 stations to measure air quality in Delhi. Next, please. We have an operational air quality forecasting system that has been providing forecasts since October 2018. We also had a system before then, but I will show in the next slide that that system was not performing very well. information dissemination is there. There are multiple mechanisms. And then finally, next please, there is this National Clean Air Program, which aims to reduce PM 2.5 pollution in India by 20 to 30%. So as you know that our efforts are primarily focused on air pollution. So go to the next slide, please. And we also had a WRF-Chem based system before we had that 2017 event. And so here in this slide, what you see is in black, you see daily average PM 2.5 based on the observations at 23 stations in Delhi. And in red is the corresponding model prediction from WRF-Chem based on first 24 hours of the forecast. And so you can see that in October, the forecast was not too bad, except 19 October, which is the Diwali day. And so we did not have the firecracker emissions. But then the model completely failed during the episode that occurred between 5 to kind of 12-13 November. Next one, please. So then we came up with a system which assimilates the aerosol optical depth from the MODIS satellite. And if you click next, then that will show you the improvement in the prediction of air quality on top of what we had before 2017. So not only did it correct the PM 2.5 predictions in October most of the time, it also reduced the errors in PM 2.5 predictions by up to 200 micrograms per meter cube during the most intense event. Next, please. So over this entire period, when we averaged, the mean bias reduction was about 86% on day 1 forecast, and about 80% on day 2 forecast, and about 70% on day 3 forecast. So the assimilation of the satellite data really helped. But then we tried to analyze why did assimilation lead to such a large improvement in air quality. So here what I'm showing is the frequency distribution of aerosol optical depth from MODIS in black, from the WRF-Chem background, which means we are not assimilating any data, that you see in red. And so if you compare the red curve and the black curve, you can see a large underestimation of aerosol optical depth by MODIS. And then when we did the assimilation, we push the WRF-Chem AOD very close to MODIS, which is in blue line. And if you look at the average values, the MODIS and WRF assimilated values are very similar. Next, please. But as you know that, maybe click one more time, there is an animation. So as we know that aerosol optical depth is a column integrated quantity. So we wanted to look at how much impact does the assimilation has in surface PM 2.5, and that is what you see on the left. And so you see over Punjab, Haryana, Eastern Pakistan, Delhi, and most of Uttar Pradesh, we had on average 50 to 75 micrograms per meter cube of increment in kind of 40-day average PM 2.5 during the episode. And on the right side, you see carbon monoxide that is coming only from the fires. So in the entire fire affected area, we significantly benefited from the assimilation of aerosol optical depth. And that increment is only happening at the surface. Next, please. And if you look at the vertical distribution of PM 2.5 changes because of the assimilation in Punjab, Haryana, and Delhi, you see that we had the maximum increment in PM 2.5 near the surface, and most of the increments are happening in the boundary layer. So this was happening because we designed the chemical data assimilation by taking into account the emission uncertainties, which had been previously missing in some of the data assimilation systems. Because we have higher uncertainties in the model in the boundary layer, that is what leads to increments in PM 2.5 in the lower atmosphere compared to the upper atmosphere. Next, please. So I am not sure if Chinmay is in the room. Chinmay has done a lot of work in making this system operational. He is the one who took care of it when we transitioned the system from NCAR to IITM. He has also done a lot of other impressive things with the system, which means like extending the system to 400-meter resolution, and developed the websites together with Soniji. So this Delhi air quality information goes to Commission for Air Quality Management, which then uses it as one piece of information to activate the graded response action plans. And so because you live in Delhi, I'm sure that you are familiar with this type of news, especially during winter time. So when there is a polluted air forecast, then they restrict activities. Next, please. And when there is a indication of cleaner air, then they go back to normal operation. And if you are interested in understanding the whole process, please come and talk to Soniji. He spends maybe all his day and night providing information to CAQM to make that decision. Next, please. So I think we have done an analysis and we have about 80% accuracy most of the time, but atmosphere continues to surprise us. And all of the air quality forecasting systems, they failed miserably during one of the worst air pollution events of this season. So next slide, please. This is the near real-time evaluation of the WRF-Chem-based forecast against observation over the last 2 months. And so you can see here, the observations are in red, the model is in blue, and except that period from 12 to 18 November, when we had the highest observed PM2.5, the blue and red lines are nearly overlapping with each other. Even the event, which was just last week, was forecasted very well. And we see a similar performance in terms of tendency for the SILA model that IMD is running. But then we were really curious, like what happened during that event? We have not seen this type of failure in the last 5 years, where we were not even able to predict the tendencies correctly. So you see that the blue line during that in that circle shows a continuous decrease, whereas the red line shows a continuous increase. So when I first saw this, my suspicion was the marriages, because 12 November was the start of the marriage season in Delhi, and there were 50,000 marriages in NCR on 12th November. So I thought, like, people celebrate marriages with the firecrackers, and we do not have a way to include those emissions into our model. So I was wondering, like, whether that is the reason. And I had no idea what else could be possible. So then we started looking a little bit into other things. Next slide, please. So one of the things that we think, and it is still an ongoing analysis, is the farmers shifted burning practices to later in the evening. So if you look at these maps of Punjab, the top row is 2019. These are one specific days, 2020, 21, and 2024. And so this is very preliminary analysis done by Hiren Jethwa. We are now collaborating with him to see if it was consistent during the whole season. But if you look at the 1 to 2 p.m., so this is like going from 10 a.m. to 5 p.m. in the evening. The satellite overpass is between 1 to 2 p.m. So in 2019, 2020, and 2021, the map that we get at 2 p.m. is kind of representative of what is happening at other hours. And so basically you can get the fire observations at 2 p.m. and assume that this is the representative fire activity and extrapolate this information to other times in your model. But in 2024, that assumptions broke down, because now you see that the fire activity at 2 p.m. is very different compared to what is happening at 5 p.m. So all the air quality forecasting systems in the world.
How you got it?
So this is actually based on a Korean satellite, which is a geostationary satellite and has some brightness temperature information. So Hiren came up with a crude algorithm to derive this information. So this highlights a strong need to have geostationary satellite observations over India. And that is where some type of partnership between MOES and ISRO and other institutions is critical, because ISRO has the satellite launching capabilities. They are doing so many wonderful things. They in fact have another product which is at a coarser resolution. It is at 3 kilometer resolution. And Dr. Bipasa Hall from Space Application Center, she has shared one product with me. So we are looking to see whether a 3-kilometer product, yes, fire location product can be used to constrain the diurnal variability of fire activity over this part of the world during the pollution season. Otherwise, we really need to work with ISRO and see if we can develop a high resolution fire product over India. This is, yes, I think it is from INSAT. Okay, so this is also a message to us, right? Means it is like you develop a system which has been performing well for certain number of years, and then one single behavioral change in the society can throw your system off the accuracy very quickly. Next, please. The other part was because the fires were so strong, we, as I said, we were benefiting significantly from the assimilation of the MODIS satellite AOD. And so these are the maps of the satellite AOD retrievals during from 12 November to 15 November 2024. And you see that over Punjab and Haryana, we do not have any retrieval at all. So because the smoke was so thick, it even led to foggy conditions. And Chinmay was telling me earlier this morning that they had fog in 18 degrees Celsius. And our thumb rule was that we cannot have fog above 10 degrees Celsius. And so it is even defying some of our empirical understanding of the atmosphere in this region. So when you have these type of conditions, then we do not have those satellite retrievals. And so not only we are not getting better initial conditions for our air quality forecast over Delhi, in earlier years, we were benefiting from the transport of those enhancements in aerosols because of assimilation. And so that benefit was also missing. So basically, we had wrong information about fires. We were not able to improve the initialization of our models based on the satellite data. So the only information that we were left with during this event was coming from the surface observations. And when the information is coming from surface observations in the assimilation, their impact goes away in like 10 days. NASA has been working on another algorithm that can better retrieve aerosol optical depth during smoky conditions. And now we are going to test if assimilating those type of retrievals will help us in this event. Another challenge with that retrieval is because it tries to go down to 1 kilometer resolution. It takes more time for processing. This product is available 3 hours after the overpass of MODIS, which means that you can probably deal with a 3-hour lag in your forecast, but that product is available with a 24-hour latency in near real time. So it means if we start to assimilate aerosol optical depth based on the new product, then we will have to start our forecast 1 day early, or we need to increase the lead time by 1 day. And then we also need to evaluate if you have initialized your model with an improved satellite products 24 hours in advance, are the benefits going to stay after 24 hours? So there are practical challenges associated with simulating these events. So with these type of limitations in mind, we have come up with another approach, and we call that analog ensemble. Next slide, please. So we say that, okay, we have limitations of satellite data. Satellites cannot see during the smoky and cloud conditions, but we have observations at 50 stations in NCR. We also have observations in Punjab and Haryana that we assimilate into our model. So is there a way for us to combine our model predictions with those observations to bias correct and post-process our forecast? So this is a technique that is very popular in numerical weather predictions. It is used by NOAA to bias correct the operational weather forecasts. We have also implemented this in NOAA for correcting the air quality forecast. So we thought, like, can we try this for the Delhi air pollution event that we just had? So in this technique, what we do is, suppose you make a 24-hour forecast. Next, please. Then what we try to do is, we try to find a predefined number of analogs based on certain predictors, right? We know that weather and air quality conditions repeat themselves. So the type of weather that I have today, similar type of weather and air quality would have occurred in the past. So next, please. So what we do is we go back in time into our entire forecast archive, and we try to find the days or hours during which we had similar weather and air quality conditions in the past. So if your model has not changed during the entire forecasting duration, you can assume that model might have made the same error in the past in forecasting these conditions as it did today. And so then corresponding to those analog forecasts, we select the PM 2.5 observations. And then next, please. And then we make an ensemble based on these analog observations. So basically, you use the model only to identify similar situations, and then you try to make a prediction, a forecast, which is deterministic, and you can also do probabilistic because we do multiple members, and then we take those members. So next, please. And so this is now the 5-day forecast for the 13 November 2024 at one of the stations in Delhi. And so here now you see that in this open circles, we show the observations of PM 2.5. In black, we have the WRF-Chem prediction, which miserably failed during this episode. And now in red, we have the analog ensemble deterministic prediction based on the 5 members. So this is again very initial result, but this is very encouraging. Remember that the event happened only 1 month ago. And so I think IITM team has been working very hard to put together the data into this format that we need to run the analog ensemble. And then our team at NCAR ran this ensemble last week. And so this is very preliminary, but this is very encouraging. And now our objective is to implement this operationally for the next season and see if we are able to capture these type of events, or are there more surprises for us in the future? Yes, AODs are assimilated here also, whatever AOD is available. Next, please. But then, so these 5 years of experience working together with IITM and IMD, by working together, we are finding new challenges. So first of all, as the graded response action plan is activated, you know that in the severe category, there is a ban on construction activities. And then during one of those bans, the labor union moved to Supreme Court asking the court to revoke that ban because it creates a challenge for them to put food on the table. Means these are the people working on daily wage workers. So it's a problem similar to the climate injustice. Like the countries that have contributed the most to climate change, they are most prepared to deal with it. So it's the same thing, right? The people working in the construction sector may be the least responsible for the air pollution problem, but they might be the ones that are suffering the most. So this is an unintended consequences of the policies that we have today, right? So it poses environmental justice and equity challenges. So we need to work with behavioral scientists. Probably we need to work with social scientists to understand how can we make our policies more inclusive. And then click next, please. And then there are scientific challenges. So MODIS is going to die next year. And then what are we going to assimilate, right? So we have been doing some experiments. There is another satellite called VIRS, which provides aerosol optical depth. There is also a ocean color monitor from ISRO. So we have done experiments by assimilating AOD from those satellites, even though we do not get as much benefit as we got from assimilating MODIS, likely because we had 2 satellites, Terra and Aqua, providing observations at 10:30 and 1:30, and we were assimilating them all together and getting the maximum benefit. But still assimilating VIRS and OCM gives us large benefits, which are very similar to MODIS. Then because of the environmental justice and equity challenges, the commission needs more accurate 3rd-day forecast, right? Everybody in this room knows that atmosphere is a chaotic system and the accuracy of the forecast goes down with time. But we need to produce more accurate 3rd-day forecast so that commission can let Supreme Court know 3 days in advance what type of restrictions they are going to activate. So it's a challenge that we have against our fundamental knowledge of the atmosphere. This is how the atmosphere behaves. But this is a challenge that we need to address. Dynamic changes in emissions, like I mentioned, the marriages, the firecracker emissions. How are we going to represent that in the model? Do we need to collaborate with priests and the people who look up for marriage dates? Do we need to collaborate people who do music and DJs and other things? Do we need to think out of the box to represent those dynamic changes in emissions? So that is another challenge. We might benefit from rapid refresh of air quality forecast, which means instead of initializing the forecast every 24 hours, we try to refresh it every few hours. But then there is a practical challenge. As soon as you make an observation, it takes a few hours for that observation to be transmitted to the website. Then you process it and then you prepare it for assimilation. You might already have a delay of 6 to 7 hours into that process. But that could be a solution. So we have to be innovative about how are we going to address those type of challenges. Crop residue burning, it is going to be a challenge unless we find an alternative to the management of crop residue. And there will always be large uncertainties in those emissions because we do not know how much biomass has been generated, what are the emission factors, how much emissions of pollutants are happening as you burn 1 kilogram of that load. So that is another challenge. And then we know that India has a smart city mission now, and there are 100 cities that are identified, and air quality, good air quality is one of the important parameters for a city to be called smart. And so soon there may be a need for having similar systems for more than 100 cities in India. And so right now, the systems that we are running specifically for Delhi, going down to 300 to 400 meter resolution, imagine, do we have the computing power to run hundreds of these systems in parallel? Or can we take help from some AI ML type of techniques to extend these capabilities to other cities in India? So these are some of the challenges that I identified based on our 5 years of collaboration with IITM and IMD. And I think this brings me to the last slide. Next, please. So with this, I'd like to thank you and take any questions.
Thank you, Dr. Rajesh. And we can take few questions. Of course, don't want to delay Dr. Rajesh in this inclement weather here, but still we can have few questions. Yes.
At 2:30 p.m. satellite pass. Based on that, you are estimating the total one-day fire count. That algorithm is there in that simulation system?
Yes. Yeah, there is a system. So basically what happens, so that system is also global. So we have a model called fire inventory from NCAR. And so once the global observations of fire locations has been made, we have predefined estimates of biomass load available in different regions and the emission factors. So we combine that information into an algorithm and we calculate the fire emissions from each of the hotspots that has been observed by the satellite. That's why the near real-time emissions of fires are delayed by 1 day. So, but now after this episode, I had a discussion with Soniji and Sachin at IITM, and we are going to talk to the developers of this model and see if we can have a regional version dedicated to India, and if we can at least have the same day fire emissions going into the model.
Yeah, small question. Does this model incorporate the firecrackers which are burned during Diwali?
No.
So I mean, if we are thinking that, like, I mean, what I got is that on 12th that episode, it's basically you are putting a lot of emphasis on the cracker burn marriages. Okay, but similar situation would have happened during Diwali also. So,
and I think that is a very important question, and we need to find a way to represent those. So I think on the wedding days, like the start of the wedding season, we haven't done anything. But on Diwali days, what we do is we increase our anthropogenic emissions by a factor of 2 or 3, anticipating that there will be a lot of firecracker emissions. But the composition of the firecracker emissions would be much different compared to anthropogenic emissions. So we need a dynamic system. We need to get information about how much firecrackers emissions might happen on a particular night. I do not still know how can we get that information, but I think it is important to get that.
Yeah. In one of the plot, when you assimilated through the MODIs, we were not able to get, we were not able to capture the this episode from 12 to 19 November. But actually, there was the two data assimilation was going. One was for the surface aerosol concentration as well as the MODIs.
Yes.
So whether when we are giving the surface PM 2.5 and 10 assimilation there, so why it was not able to capture within the for 1 day?
So I think the problem is with the density of the networks that we have for the surface stations, right? So you assimilate, at the time of assimilation, you will go very close to the observations, right? And then you start integrating your model in future, right? So the winds will start taking this impact downwind. If you do not have improved initial conditions in upwind regions, then those errors will start affecting your stations. So I have talked to Praful, who has looked at up to what time we retain the benefit of assimilating surface observation, and it's only 8 to 10 hours. So if we increase the number of stations spatially, then we can probably get a better benefit. But with the current network, we can only benefit only up to 8 to 10 hours. So the forecast starts at 5:30 p.m. IST. And so you do the forecast, which starts at like 9 UTC, corresponding to the satellite observation time. And by midnight, that influence has gone.
So actually, right now, Miss in Delhi, we have the 50 stations. So do you?
No. So it is not only about Delhi. Delhi is a very small area, right? So when the biomass burning plumes are coming, then the influence, capturing the influence from Punjab and Haryana and maintaining that plume is very, very important. So if our measuring network does not contain that plume, then we are not going to have that benefit. So where we had benefits earlier was that we were constraining the spatial distribution there as well. Like the plot I showed for PM 2.5, we had highest increment over Punjab. So with the wind, that benefit was also coming. And so we even had improvements in the third day forecast because of that. So satellites helps us better constrain the entire spatial structures. And I think in situ observations will help us better constrain urban emission sources, their impacts.
Yeah.
What meteorological phenomena will explain more that failures. Because see, if you're seeing the NCM 330 meter and models, the models are, and your fire count things not much there in the NCM. But it is also still cutting the things, and you are getting the same trend. So I'm thinking meteorology may be playing more role in that than this generation.
So that is correct, sir. But I think capturing the aerosol load in the vertical, it is very important for capturing the weather parameters correctly, right? I think there is a feedback loop that is happening here. Say we have a lot of emissions that happen during the night. So when next morning the sun comes, it encounters a thick aerosol layer. And this thick aerosol layer blocks the solar radiation from reaching the surface, which means your boundary layer gets shallower. And so if you have the same amount of emissions, you are adding more emissions, and now they are increasing the surface concentration, and you have more load. You go to the next day, your boundary layer is further shallower, and then you keep this mechanism until you have some type of large systems like Western disturbance cleaning it up. So if we have the AOD measurements, that really helps us capture that load better. In the paper, means I didn't show the graph here, but we see an improvement of up to 3 to 4 degrees Celsius in temperature forecast because of the assimilation of AOD. So weather patterns, they derive the air pollution episodes, but there is also a feedback loop that determines that the feedback between the boundary layer and the aerosol radiation interactions. So unless we capture that, because otherwise, during this 12 to 18 October episode, the winds were strong. all models were showing that, and that's why there was a dispersion. But that stability of the boundary layer, that was happening because of this thick aerosol layer, which is visible in the satellite data, was not captured by the models. But yes, weather pattern, you are right. Means if we have a good understanding of weather patterns, we have a better understanding of air pollution.
Okay.
Right. So you told that you at present you are doing only chemical simulation, right?
Mhm.
So why don't we try like a combination of both chemical and atmospheric simulation?
Very good question, and I think we should do that. I am not an expert in the meteorological assimilation, so we probably need help from Sir in doing that. But I think what we do is we take the initial conditions and the boundary conditions for meteorology for our system from what Sir's group is producing. So they come from the IITM 12-kilometer GFS forecast. And so we do have some combination, like some impact coming from those initial conditions through the IITM system.
Yeah, that's one more question is like, especially when we are looking the bond layer dynamics in WF Chem. So especially for chemistry models, what from the literature, what I found is like, especially when you go with the closure techniques.
Mhm.
So when we go for the closure techniques, giving more pollutant load over the particular region. So that is already proved in many literature already. So especially when we're running at the pan-Indian level, like at higher domain level. So that time, are we really using like chemical? Because at the same time, what happens when we don't have urban kind of situation.
Mhm.
So that time, okay, your local closure techniques will be well good. But when go to the rural kind of environment, so that time we don't have closure techniques works very well. So can you do this like a blending of these two? Because that actually from Chennai also a lot of time I discussed that. So can we tweak the model in such a way that over the urban regions, closure techniques will work more better? Like it's a combination kind of thing. Can we do?
Sorry, closer means closer.
Like the bond layer.
Oh, so you mean local versus non-local?
Yeah,
schemes?
local
Yeah.
versus non-local.
Okay, so I think so. You are raising a very good point. I think what you are pointing to is we need a dynamical ensemble system,
Yeah.
right? And so we need that for sure, right? We should have in our ensemble, we should have some non-local schemes, some local schemes, but we have to be careful when we design this ensemble system, is that we need to take into account, we should try to represent all sources of uncertainties in air quality simulations. So weather is one part. So I think we need some sort of multi-physics representation in our ensemble, some sort of multiple initial condition representation, emission uncertainty representation, secondary organic aerosol representations, fire emission representations. The challenge with that approach would then be we might end up with 100 ensemble members, right, which will be impractical to run in operations. But we should not be discouraged by that. There are techniques now using which we can down select which ensemble members can objectively reproduce the variability of the ensemble. So this is in our future plans. But your point is well taken.
Thank you.
I have a question. This is Madhulata. Thanks for interesting seminar. In one of your slide, you showed the AOD. I understand from the model, if it is greater than 500, always there is tendency model is not showing. So the episode you selected is historically most polluted, or means previously any episode is like that you tested it? Because from your slide I understand that if it is the thing, maybe in the model.
So I think what I have found that is, so generally, historically, most of the models, they underestimate aerosol optical depth over this region because maybe they do not have the correct emissions. They do not have all the processes that are needed to appropriately simulate aerosols in the model. So there could be multiple reasons. And then, so what I have found is if the AOD is below 0.6, then the aerosol radiation interactions are probably not that important. for the feedback point of view. As soon as it goes above 0.6, and I have done some analysis, the errors in the temperature predictions and the AOD, they correlate 1-to-1. So in some of my preliminary research, I have found that the aerosol radiation interactions become critical above the AOD values of 0.6. Now, the issue that happens is when the AOD is 0.6, it means like very polluted conditions. And that aerosol burden is very, very high. And so if you are not capturing the aerosol load correctly, the boundary layer simulations will be wrong because the model will be simulating a more deeper boundary layer. You will mix your emissions into a larger volume. And aerosol optical depth assimilation is helping us address that part of the problem. So the episode that we simulated, we found that nearly 50% of the improvement in the simulation came because of the improvement in initial condition, and the remaining 50% came from aerosol radiation interaction. So if we do not constrain the aerosol load, or if we do not have model inputs that give us realistic AOD values, we are never going to get those interactions simulated well. And if we do inverse modeling type of studies, we might end up overestimating the emissions.
Thank you.
So we have any more question? I think no.
So there's a question in chat box.
Chat box, that question I can reply from Menka. This presentation is available, will be available on our IMD website. So you can have a look at that PPT again, and this lecture will also be available. This video lecture will also be available on that day.
Sony sir, namaskar. Sir, I have a question.
Yes, yeah. Durai?
Yes, sir. Yes, sir.
Yeah.
Thank you, sir. Sir, my question is, the low-level wind shear alert system uses anemometer to measure the wind shear near the airport. So my question is whether the low-level wind shear means the horizontal wind shear or vertical wind shear.
So I think they also have the Doppler weather radars. So I think they measure it at multiple levels. I'm not an expert in that, so maybe I can go back and ask my colleagues, like at what levels they make the wind measurements to correctly answer your question.
Even I wanted to ask that question to you, because in Mosam mission, we are making a big investment in improving the aviation weather services, and this low-level wind shear alert system is one of the important component of that program. So if you can send us more information about this system, then that will help.
What I can also do is I can arrange a 1-hour seminar that can be done online to this group by the experts who have developed this low-level wind alert system.
Yeah, I think that will be really nice to understand this system.
Yes, sir. Yes, sir.
So,
normally we use Doppler weather radar for the, detecting the low-level wind shear. But this one, as he mentioned in that PPT, low-level wind shear for measuring the wind shear, the low-level wind shear. So my question is, the low level is horizontal or vertical? So
yeah. Unfortunately, I do not know the answer to this question. It was just to highlight that we have this capability in the lab, but I can get you in touch with the people who know how it works.
Okay, sir. Thank you very much.
I have a question. Continue. Actually, I wrote this. So basically, it explains about the cold pool of the system. Thunderstorms now, cold pool of the system. And in how much advance you are giving this warning? And how much lead time?
I also do not know, but I think it is less than an hour.
Observation.
Yeah, it's observation based, means like it is linked to the cockpits somehow or through via ATC, but I can get experts who can answer all these questions.
I have one more quick question.
Go ahead.
So you mentioned about numerical test beds, right? You have so
Yes.
many. So on an outline in NCAR, what you do?
So basically, like, so NOAA has, say, for example, the Unified Forecast System development ongoing now, and they want different physical parameterizations to be so that they are model independent, right? So there is a system called CCPP, Common Community Physics Package. So some of the work in our test bed goes on making sure that these physical parameterizations are coded in such a way that they can be plugged into any system. And then we have also developed the MET Plus system, which is the model verification system that is also developed under the Joint Numerical Test Bed. Is Hurricane WRF also, which is now being replaced by HFAS. So these are the activities that are happening under the test bed.
Thank you.
The first slide, climate related vulnerability both in South Asia or Africa. What is the reason?
It is the also, so one reason I can say is that we are located in tropics, right? So as the atmosphere is getting warmer, the atmosphere can hold more moisture, right? So the humidity increases. So basically the wet bulb temperature, which is it depends on both temperature and humidity, that is more severe now. Means you can feel that in Delhi too, right? You have dry heat during April through maybe mid-June until the monsoon comes. And so that has a different level of health impact. And then as soon as the monsoon comes, it's a combination of heat and humidity, right? So that is one reason. Another is the infrastructure, right? People in the developed world, they go into air conditioning, means they have air conditioning even into their public transport system. And so their infrastructure makes them better prepared compared to some of the developing nations. So it's both the resources and the impacts of climate change.
So let us thank Dr. Rajesh for this wonderful talk and discussion. Now I would request Dr. V.S. Prasad to deliver the 24th lecture of this series.
In the first instant, I would like to thank Director General Dr. Mahapatra for giving this opportunity, and also thank Dr. Soni and Anup. Dr. Soni and Anup for inviting me for this lecture. And as Director General mentioned, that NCMRW of NINA to introduce into the this IMD forum. All IMD people know that NCMRW, we are working together. And I thank Dr. Rajesh. He gave almost many points as an introduction to this one, the unified system, CSPP, and also data assimilation, importance of those things also he mentioned that one. And I want to now introduce the seamless weather forecasting system that includes from the city scale forecast to the climate models that we are developing at NCMRW. And all these products are available to the these NWP things. And NCMRW is a part of is already a part of the 158 celebrations. We conducted 30 years of operation NWP and 150 years celebrations on 19th of last month. IMD is involved in that one. We are celebrated more than 10 countries representatives participated, and there were 30 foreign participants, and there are more than 150 people presented that one. And say there also we presented all those things. So for the sake of getting to the all IMD people, I repeat the presentation here. So next slide. See, this is the mission that center was put up, that one, to develop the modeling and data assimilation. And if you see that one, this one, we have to the mandate to underpin the national forecasting capability of IMD, and we are doing that one. So we are part of that. We are partner with IMD, and we are working together for getting when most of the things working for the NWP and strengthening the weather forecasting system in India and making India as a weather ready nation. Next slide. So from last 30 years, I'm repeating that one, and the acceptability of NWP products in IMD is dependent on the second points. These models gives only guidance. The forecasts are given by the humans and forecasters. So model doesn't give the forecast. And morning, just before this one, we are in the director's DG's room. We're finding that direct DG is representing many, many models and representing in that one and getting the good forecast that one. The other thing is what NCMRW contributed is the agro advisory services that we developed for the 120 agro meteorological forecasting units. The concept was developed and NCMRW was set up for that one, for giving the weather forecast for the agriculture purpose. And we developed 128 agriculture and that declared as a successful system, and the system was transferred to the IMD when the MOAS is formed, and it is working very successfully. And agro advisory services and IMD improved a lot, and many people started working involved in that one. And the other thing I had CMRWF, you all know that IMD, GFS systems, we have played a very important role. NCMRW is the legacy model of NCMRWF, and the data assimilation part of also we are supporting that one, and that became now using in the IMD models. Now the NCMRWF playing other major role is data assimilation. Not only atmospheric, we are now doing land, ocean, atmospheric systems, and these developments together now we have about to develop a seamless weather forecasting system with the coupled model that I will introduce to. Next slide. So earlier, if you are finding that there are a lot of jokes on meteorologists telling that what are the happening in the thing, the forecasts are not that much accurate, and many places you are finding that one. Next slide. Next slide. And you find now we are able to simulate the global weather, almost similar. For analysis, even satellite picture, we can see there are almost all the systems at major scales are reproduced very well. This is the strength of our simulation system and model system. We are able to simulate major features of the present day weather reasonably well, and this is demonstrate that one. Next slide. And now our forecasting system, earlier we are giving the deterministic forecast system and we are not giving the uncertainty to the forecasters. Now we are running 21 member NEPS and GEFS systems, and with that we are able to convey our stakeholders what is the uncertainty in our forecast. In the right hand side you can see the range, the possible range, and also the deterministic quantity. So now our systems became much more informative. People can judge the risk that they can take. We are not only giving the forecast, we are also conveying the uncertainty at this point. How it became possible? Next slide. How it became, it like that we are giving throughout the globe. You can see this one for the next 10 days, we are giving the system with uncertainty and the quantity of the forecast. Next slide. So the forecasts have become more popular, and likewise demand is there. Earlier we are giving the only 24 hours, 12-hour forecast or 20-hourly forecast. Now the demand is more. We are giving the scales from the nowcasting, that is from minutes, hours, and to the day, and also being the outlook for the week and month, and also our sister organizations, IITM, giving the years and decades forecasts also. So what we give these different stakes of forecasts are demanding there. And in the case of nowcast, we are giving the quantity and uncertainty. The probability we are giving that, uncertainty we are giving that one. Where if you go to the seasonal and sub-seasonal forecast, you know we are giving the tendency, because we have a lot of climatology of the models from the available from the models, and thereby we are giving the tendency and uncertainty. These all things where we are around for 15 years back, we are giving the single day 24-hour, 48 forecast. Now we are giving the all scales of the forecast, develop these things, and we know we are running the HRR, what he mentioned earlier for the climate, high resolution rapid refreshes, and also we are running the electric forecast, WRF-E, and also giving the lighting forecast. So all scales of the forecast, our models are able to with our modeling systems, or we are able to give the our stakeholders. Next slide. And all these are probable because of this is the numerical model. Numerical model is nothing but we have the atmosphere is continuous, but for modeling purpose we have make it as gridded at different grades, that horizontal resolution and vertical resolution. And also, if you see that every grade, the physical phenomenon, what is happening is it is independent of the grid. So all the physical processes we have parameterize, we have to parameterize this one. So in the model, we have the dynamical core, that is Laplacian equations, which will be solved mathematically. And to become more realistic, we have to put the realistic physics in that one. We have to not only that some boundary conditions that are coming from the ocean surface, and also how the radiation transfers and all those and fluxes. Not only that one, we have to see the cloud parameterizations and the subgrid process, all these things. As much as we improve that one, the forecast quality improves. The different ranges of forecast is possible if you increase the resolution and if you increase different physics based on if you are able to use the cloud resolving models for giving the no casting and high resolution forecast, and whereas for the medium range and sub range forecast, our resolution can be a 10 to 20 kilometer model. And as you are changing the resolution, we have to do the dynamics also have to be changed for the hydrostatic to non-hydrostatic equation, non-hydrostatics, and all these are in our different models. Next slide. And in this parameterization, what we include, we have to become more and more reasonable, realistic when we want to get the high resolution prediction. Not only the high resolution, we have to resolve all the physics and physical packages in that one. And the efforts are going on how well we represent the physics in the scales and how much resolution will increase for capturing the frequency and the things. Next, please. And these systems, if you use initial boundary, initial case, we'll get the numerical weather model, and same time if you are allowing to change the ocean parameters and also land physics and also atmospheric composition, it will become a climate model. And all type of biology, the systems have become more complex. We have a Earth system model where not only ocean parameters, not only that one, we have land use, land changes, and also plant ecology and ocean biology are included to become a much complex Earth system model. So we have the same model with different resolutions. If you solve it as a initial conditions, we'll get the weather forecast, and if you use with the changes of the fluxes and boundary condition, you will get the climate models and Earth system models. Next slide. And to make it a numerical model, at NCMRWF, we are more interested in, we are mandated to give the weather system. So it is a initial value problem. And we are, for that one, we are made a big, the NWP system requires the observations, receiving, addressing, and data processing, and the NWP model, what I mentioned, that type of things, and post-processing to give the models are available. As earlier speaker mentioned, it is required to get the data of the observations at a realistic time so that we can produce the initialize the models at reliability. So a lot of efforts were made at NCMRWF, and with the help of, next slide, with the help of IMD, we were able to get the system. In the case of GFS system, what you mentioned, IMD is running, we have the global model running at one dynamics, and we have WRF and what mentioned the chemical model, and also it is given by that one and seasonal model. Different dynamical cores are there, so the model is not unified, and we have to interpret the data from the GFS system to the, if you are running the WRF, you have to change the regrid the things, and likely to different models, we have to do the regridding and use that one. Next slide. In the next slide, please. This I'm skipping. And in the case of these things, we have the resolution. We started with a 120, 150 kilometer course resolution things, and gradually we now are on to 12 kilometers high resolution model, and it is possible because of the evolution of the computing infrastructure that our ministry and government are doing. We are changing from the 12-bit system now. Recently, we acquired 20 petaflop system, and Prime Minister Modi inaugurated the system recently, and we are the changes required, and the physics and the resolutions are possible now with the high resolution computing system available with us. Next slide. And this shows that with the resolution, how our models are evolved, and we are reaching different scales of models over the time. And you can see the changes from the coarse resolution to 12 kilometers is possible with the computer capacity that we are increasing over the times. Next slide. And this is a system with the increase of computing system. Now we implemented unified modeling system, in which earlier we are seeing the GFS. We have to different models we are running with different dynamics, and we have to do all the interpolations of things. Here, the unified model, same dynamical core we are using for the starting from the 330 meter city model for pollution and visibility forecast, that thing, to 12 kilometer global with 21 ensembles, and also 4 kilometers regional and 65 kilometers coupled system. These are all having the same dynamical core. And depending upon the resolutions, we are using the different physical packages to resolve the resolve the weather at the scale and the frequency at which we are reckoning that one. And the coupled system, we are using 65 kilometers. All are having the same dynamical core, and we are called the unified system. And we had that NCAR. Now they are going for this unified type of systems, and we already from the 2012 onwards, this unified system is in place with us, and we are generating with this one seasonal, sub-seasonal forecast to the all regional forecast with a more accuracy. Next slide. And not only that thing, increasing the data, increase the resolution of data, we have made many efforts with the help of IMD. We have started getting a lot of GTS data from that one. Not only that one, we have made many arrangements. You can see the pie diagram where how the data volume increased over the years. And the blue line shows the satellite data, green line says that blue line shows the GTS data, and the pie other diagram shows that the volume of the data will increase. Lot of improvement was done in the data reception, and now we are you can right hand side, so that we are almost equivalent to ECMWF, and we are getting the equal amount of data like any other global NWP center, and volume is increasing. This is next slide. This is became possible because we made efforts to receive all the data from the satellite data producers from NOVA, UMET, we made special arrangements, and we get the data from all of the sources within the reasonable time. And we are also getting the with Japan and Korea and all over the world, we're receiving that various satellite data sets, and all the data is processing here. Next slide. The important, we have getting all the data. Data for doing data assimilation, we should have an understanding of the observation. See, the models variables are fixed. We have the only the 5 model variables, and the observation may not be represented from the model variables. Here you have see the hybrid value equations where you are finding the H, the observation operator. This operator converts the model prognostic variables to the observation that we receive. So with that, we can assimilate any type of observation that are related to the model. From satellites, it may be radiance, it may be the horizontal wind, or it may be a radio occultation. Whatever orbiting, we can convert this observation, this model variable to the observation, the increment will assimilate into the model. This is called the variation analysis system. You see the complex diagram that shown on the right hand side, how the observations are received. We know that all observations are observational errors will be there, and there will be the representation because we are doing different grids. There will be the representative errors, all those things we have to address that one, and the process the data, receive the data, we'll get the different formats, and everything we have to convert it into the proper format, and we have to develop, understand the observation and develop the operator and run these assimilations, use it in the assimilation system to get the regular observation what we produce on the top right hand corner. So the data assimilation is the thing, is the understanding the observation, understanding of the model, what are the errors are possible. So model errors will be there, and also we have to understand the different kinds of observations so that we can use that to simulate the model, and that will be used in generating. Next slide. Next slide. Like that, we have the ocean simulation system also. Next slide. Next slide. And land data, different extended Kalman filter data is there. We have the land data simulation system. As atmospheric, ocean, land data assimilation systems are implemented, are in place at NCMOD in this one, and we are developing these things with different model observations, assimilating them into the next slide. These are the all observations that are being assimilated in CMRW, and you can see now the lot of satellite data sets are being assimilated, and some of the Indian satellites, we are the first to use that one, and I will give the details how to assimilate this data in the next slide. And these are the pie diagram. You can see the 90% of the data what we are assimilating now satellite data, and then about 10% is the conventional data that we are assimilating, and most of the data sets are you can see the satellite observations, radiances. These are the most high value data that we are getting that one. And next slide. And here I want to explain that one, how we can develop a new operator for using in the data assimilation. This will show AOLS recently this Europeans launched the satellite, and of course the satellite is now life is over, but it has given the new observation, what we call wind observation, but this wind is different. This wind is horizontal line of sight of winds. It is not direct wind. So it is give the profile of the horizontal winds and like radio Sunday, we are getting all the winds. And this wind, to assimilate that one, how this wind is represents the your zonal wind or meridional winds, the components. That is the operator. Like for radiance, radiative tensor is the basic operator. What is the handling that one? Here it is simply I choose this thing to explain how an operator can build very simple that one. Next slide. This is the way the observations will receive the horizontal wind. It's at this scatter that AOLS satellite passes. Then when on the right hand side you can see where the line of sight of winds are observed. These line of sight, next slide. These line of sights of winds are received about 14 or 15, 16 satellite things per day, and then we can get the ascending and descending paths that are separated. These observations are these are the type of observations we'll receive from the AOLS. Next. And these observations, we are getting to the scatterometers, the Rayleigh scattering that people we know very well, and the Mie scattering. The Rayleigh scattering will give from the lower boundary layers, and upper the Mie scattering will get the tropospheric winds, and you get the quality of the winds. If you see the RMSE error, we are getting almost very good profile. We are reaching that one. The quality of the winds are very good, and so we can use that models. Next slide. This is the operator. So we are getting the winds from the satellite, and that winds are horizontal, not the regular winds that we use in the model. So what we have to do is, from the model, we have to derive the same wind, what we observed. So the model model forecast, first guess are interpolated to the observational grid, and you get that one. So how they are related? The HOLS is related to the like the U sign. It is the way that we can horizontal wind, we can get that one. That is minus U sin theta and V sin cos theta. This is the simple operator. In the case of winds, this is the operator that converts our grid winds to the line of sight of winds. And what we'll do is the direct observation will not put assimilate that one. We take the difference between the observed and the first guess generated winds. The bias will that increment will produce. That increment will be the assimilated in that one. Like that for about radio occultation, the bending angle. The bending angle we can do that one. So by understanding any type of observation, we can do. Similarly, if you have the radar, the reflectivity, we can put how the reflectivity will give the different parameters. Like that, from the observation, from the model parameters, if you are able to simulate any observations, all the things we can integrate on. Even we can simulate GPS signal also. That is what we call the GPS, that integrated water vapor will do that one. So GNSS thing. So any new observations, this is the way the research will go on, the data assimilation, and all type of new observations we can assimilate and get the improvement of the things, because the conventional observations, number of conventional observations are reducing that one, and we can work on understanding the observations and how these observations are related to the model things. We can develop observation parameters, and this can be assimilated to the model. Next slide. So we do, NC model is the second operations NWP center in the world to assimilate this HOLS data, and we studied that one. What is the impact is that one. To study the impact, we have the forecast sensitivity of observation FSOI there. It is from the 4D hour of an simulation, you can generate that one. We can see number of observations on the right hand side, shows the number of observations, and the left hand shows the how much impact it will take. You can see almost HLOS is giving the impact of the about the fifth. I think the one of the highest impact giving observation, and it is very important. That's why, and we are proposing that we should have this HLOS type of AOLS type of sensor for getting the wind data, and the importance of the wind observation can be seen in this FSOI thing. About I think it is more around about 5-6-7% improvement is coming out of only HLOS data of single satellite. That one. Next. Similarly, we can study the impact of the data differently from what we call OSC, in which observation denial we are doing that one. With observation denial, we had developed the scorecard. The green one shows the positive impact. You can see the blue one, the neutral, and other things. So we can see the lot of impact in all levels that we are getting with the HLOS data that we can assimilate. So this FSOI and the OSSE, it shows that importance of the wind observations that are required, that can be improve the forecast over, or not only in in tropical region, all over the globe. We can see the various regions also are showing that one. Lot of impact is giving. So this shows the importance of the assimilation and the observation. Next slide. And this experiment, in this one experiment was conducted by single observation. It's taking the radio sound observations and also the same place removing the radio sound observations, and nearby the observation from the AOLS was placed in that one, and see the impact. So it clearly shows, this figure clearly shows that the single experiments that AOLS is able to produce that profile that is able to produce radio sound impact more same as a radio sound, and also this moreover that it will goes upper troposphere, upper troposphere layer. The impact of AOLS wind is much more better than the radio sound. So spend with this type of wind sensor itself, we can get the impact of the many radio sound days. So this shows the cost effectiveness of the satellite sensors that we can have, that one. And but only thing is, this is a active sensor, AOLS, so it requires a lot of energy. Keeping such a satellite at a higher level is a more still technology problem, and hence the replacement of AOLS is not there. And we recently there is a conference held in IITM where we are trying to build the AOL plan for such a satellites. And the sense technology is available only for keeping such a satellite, such a active sensor in satellite for a longer period where economical benefits will be more is a difficult task. And this experiment clearly shows that radio sound, this AOLS improvements are similar. We compared to the hundreds of radio sound experiments, this AOLS profilers will give more things. Next slide. And these are the publications on the AOLS data that NCMRW did, and about for more than 5 publications came, and we demonstrated with that one, and NCMRW with the second center in the world to make it operational AOLS data at the time. Next slide. And like that, NCMRW is working in using many Indian satellites. This shows that starting from INSAT 3D to the experimental recent Meteosat 2B, how different satellite sensors are being used in NCMRW, with that all observation operators are developed, and all the satellites for the first time assimilated in NCMRW. And INSAT 3D, and myself worked on the high trace element and the observation quality improvements of the sound data. And microsat and megatropics, and so we proved that sensor is more valuable, and many people accepted the sensor, and scatterometer also. India is one of the successful sensors that have been accepted. The other global and NWP centers also, the quality of the things, and show that one. I think here Madhulata also worked on the microsat to be, I think, megatropics things, and yeah, Safir things, and also I think Raghu also did INSAT 3D things. He worked with one, and many IMD scientists worked with us for demonstrating the usability of Indian satellites, and we are working closely with ISRO. Next slide. And you can see in the case of AMVs, when we launched AMV first, that started looking into the AMVs of INSAT 3D, the Meteosat, we are getting 5 meters per second, the RMS video we are getting. At that time, we started with AMVs about 11 meters per second, and NCMRW with SAC Ahmedabad worked together, and we did a lot of experiments, and also NCMRW initial condition, first guess conditions were given to the made available to improve the forecast, and a lot of development. This data assimilation system not only use the data, it will give the feedback to observations, how to improve the observations, and how better we can do that one. And the sensor designing, these things are also possible with the first guess, the operators that were available. And this clearly shows that how much improvement is possible. And over the years, from the 2011 to 2014, with close cooperation between NCMRW and SAC Ahmedabad, we improved our INSAT RMS 5.2, and we have found the stability of the satellites have been have problems. So the retrievals are confined only over the Indian region, whereas other satellites were getting the total hemispheric things. So all the problems are identified in the data assimilation, in the data processing, pre-processing system, and this way we can contribute not only use the data, give the feedback of the data, how to improve the observations. This is possible with our simulation system and seeing the data. So that's what that NWP, not only this one give complete understanding of the observations and how to improve that. Next slide. Similarly, the radio sound in situ observations also. In situ observations of our RSRW earlier not being accepted by the other NWP center because we see a lot of errors are coming in the red line. The blue line shows that number of profile data sets, number of radio sound stations, and the red line shows the RMSE. Earlier, if you see that RMSE at our radio sound centers are very high, not being used, and lot of in the modernization of IMD, the radio sound data quality is very much improved. Almost see the RMSE almost touching is parallel, very near and parallel to 0, and the observation quality is improved, and that is approved. And we can see the changes in the observations network that also being thing that one. And recent past we can see a lot of improvement in the RSRW data of the IMD, but same time shows a little increase in the RMSE error. This may be because of the new stations that are coming up, and the new stations require some tuning or that, so that type of thing. So the simulation system give feedback to the observational, not only uses observations, give the feedback what is the increments, what is how the observation quality and what are the requirements are coming that one, and also the OSSC observations where the data has to be placed. These things, the feedback that models, simulation systems and models gives will improve the understanding of the observation system, where to place the observation, what are the requirement of observation. These things is developed, it can be explained in our data simulation systems. Next slide. And similarly, to make the quality the same thing, if during the COVID time, we know that there is no much aircraft data being used. Like that, there is a decrease in the number of observations. But to sustain the quality, at the time, a lot of efforts are made to use additional data and a lot of radio occultation data from the cosmic and other METOB and other RO data. We made additional effort to get the data and the quality, try to maintain the quality of the forecast. So this is the way the observation space, as Dr. Ravi told earlier, to sustain the forecast things, the observations, the initial conditions has to be maintained. That efforts are parallel. When we are doing parallelly, then only we can give the reliable NWP forecast. Next slide. And this way, we are continuously from the last 2018 onwards, we are conducting the FSOIs. All results are compiled, and we can see the changes in the impact that observations are creating and the change in the observational networks, so that through WM other forums to maintain sustain the observational network, we are giving the feedback to the CGMS and also our weather agencies, where the deficiencies are putting the observation network and where efforts are required to get the same time. There is the economics also there. We can spend a lot of money on the observations. So which type of observations we have to enhance? These FSOI type of experiments, what we conduct here, will give the feedback in maintaining the observational network of the country. Next slide. And similarly, morning he mentioned that for running high HRR things, we require the data at a threshold time less than 1 hour. So to receive the data at less than 1 hour, through WMO, they have the HRPT network are there all the country. To get the data within hour, the DB network is initiated, and India, with the help of NRSA, INCOIS, and IMD, we are also part of the DB network, and we are receiving all the data at India and surrounding regions or globally also within half an hour. So the using this modest data, what you are getting that one, and also NOVA, VARS, all these data now we have made with the DB network. Within half an hour we are receiving the data. So this data is available, and with that we are doing the high resolution rapid refresh things, more realistic and possible. Not only radar data, the satellite data also we are receiving, which can be used within our HRR, high resolution rapid refresh systems. So we are part of that one under most mission, and CMRWF is working closely with IMD and NIVOT to put 2 DBNet stations, one at CMRWF, one at South Chennai, so that Indian data, not only the NOVA satellites, even Chinese, Russian, all satellite data to receive within half an hour, so all polar orbiting satellites. These efforts are made. So within 6 months or so, we will get, in India, we will have 3 HRPT stations, one at Hyderabad in Koes, one in Delhi, in Noida, and other in South. We're getting this one. And we can give this data for WFChem also to see that one, so that the rapid refresh, what we are planning for all the things are available. Next. Not only for model improvement, it is not only the data and initial conditions. What I mentioned, that we are going for more and more high resolution data. We have to, there are improvements are required for physical process also. In this direction also many works are coming. Next slide. And recently, my colleagues are working on the CASIM microphysics, the cloud aerosol interaction with the microphysics. Those things are put in the things. We can see the in 4-kilometer regional model, we put the CASIM, and you can see the improvement that the triangle shows the improvements. And you can see in all ranges of low intensity to high intensity rainfall, there is good improvement in the precipitation is there. And next slide. Similarly, when we are using this thing, not only the improvements are coming, the vertical structures on the these hydrometers also. You can see they are shown that with various physics, we are getting the correct representation of hydrometers in the vertical levels. And this graph shows that various parameters that are coming that one. And to demonstrate the importance of the thing, we have taken the case of cyclone Vayu, how this new physics, which is improving the microphysics improvement, what is the impact that is coming on the cyclone. Next slide. We can see that the Vayu cyclone has a recurvature, that one. All the many models are showing that one, but one simulation is shown that it is, instead of taking recurvature, it is going straight and hit the Gujarat. The same thing, a model without changing any initial condition or thing, only changing the microphysics, and that one, we are able to simulate the recurvature of the Vayu cyclone. This shows the importance that the thing, that microphysics and steering current improvement because of the improvement of the hydrometers and apparate steering flow. The thing, we are able to steer the cyclone. Here there is no change was made in the position of the initial conditions. Only with the change of microphysics, we are able to go simulate the recurvature of the cyclone very well. And this is also the major other improvement we are showing. Next slide. Similarly, with the improvement of this one, our lighting prediction system has been, we are seeing that improvements. All the models we have, PR92 and other Lopez schemes are there, and these 2 schemes are not applicable to our Indian region, because in PR92 in the cyclone season, it is using the cloud top height. In our monsoon season, we have the very low level clouds, and also high level, the cloud thickness is very high. So the PR92 scheme is not working for our region. Similarly, the Lopez scheme, what we just the amount of humidity that we have, not able to not able to simulate that one. So the revised scheme was developed for Indian region by Dr. Saji and the group. They multi-physics, that type of option, that type of things have been put into that together by it. And the improvement was they stayed to check the how to get the lighting. Next slide. And you see, the first slide shows that with PR92 without modifications, you will get the lightning all over the country. Observations are shown that very limited to northeast, eastern part of the India, and whereas the original schemes, if you see it is giving all over the almost everywhere we are getting the lightning schemes. And similarly, pre-monsoon we are not able to simulate the lightning over the Kerala, other regions. Next slide. So by these micro multi-physics options, we are able to simulate with giving the correct weightages, we are able to simulate the lightning to reasonable extent. And it clearly shows that observation is that what are the same day, earlier we were seeing the lot of excess lightning appearing in the simulations. They are very much controlled, and now we are getting the lightning or the regions where it is occurring both in pre-monsoon and post-monsoon season. And this, next slide. This thing we are operationalized, and we're giving, of course, still improvements are required to simulate the point observation, the lightning stakes at the same with more accurately that one. So we are now that areas we are giving the most possible this as a extreme possible region, high region, moderate, like that. We are able to simulate that one, and reasonably we are giving that one. And this was demonstrated. This was very much agreed. The forecasters of IMD are using this lightning predictions from the model more reasonable, and the forecasts are improved. So next slide. Similarly, this type of work are going that one. So in the modeling side, we are working on the data simulation, putting the more observations, improving the things from the simulation schemes, and also using new observations. And then we're also working on the improvement of the physics and giving the reasonable forecast and improving the forecast. And you can see we demonstrated in the case of lightning and also cyclone. We are working on how these new microphysics with double moment and COMAF. These are still works are going on, sir. We are expecting more increases, more improvements in the physics are possible, and many works are going on that one. Next. Similarly, for the city model, we developed a 330-meter city model for Delhi, where the urban morphology and irrigation, these are included, and in-house we developed using the Indian satellite things. With the help of IRS Dehradun, Delhi urban morphology is developed, and we included that one. And land cover also developed and included. And next slide. Similarly, the irrigation was included. We can see a lot of improvement after including the irrigation. Next slide. An improvement are going. So these are the developments are carried out, and this is the timelines what I'm showing that. And same, we started from the coastal resolution 150 kilometers and now reach 220. This is the timelines, various scales what we have achieved, that is shown that one. And next slide. And the simulation systems, what I mentioned, that develop various stages that were done, and we can see almost with very frequently the simulation systems are updated with the models and schemes, and various state-of-art techniques are being used. And now hybrid 4D hybrid ensemble war, the high resolution things at 12 kilometer ensembles, we are using that one. So all these developments are made possible with the computing powers. Next. So the next one is the ensemble prediction system that I mentioned. That one we started even in the 90s. Now operationally we are producing one of the India is in 2017, we are the highest resolution ensemble members that were producing resolution, and still that work, a lot of work is going on. We're increasing the ensemble prediction. Next. So this is the regional models. I'll skip this one for the want of time. And this is the improvement we made possible with all the techniques, that the forecast quality is improved. And it is not only our self-satisfaction. You can see in that NOVA monitoring our forecast system quality. It is next to almost the topmost line is ECMWF. It is leader, undoubtedly leader. After that, we are, all the models are almost same, and we are also in the same thing. Our quality is almost with the all other developed countries. We are almost same, or for our region, if you take, we are much better than them in the case of Indian region only. Next. So with these improvements, we have carried out a lot of improvements for model, and 2017, we have a lot of improvements are shown. And because of that one, we run the reanalysis starting from the 1979. We run the reanalysis, very high resolution for regional, and the global reanalysis. We run that one, and the data is made available. Next. With this reanalysis, we studied the heat wave. Next slide. With model, and we are able to produce the heat waves according to WMO definitions, and it is clearly objective. So we are able to identify the number of cases, and according to the definition, the top one shows the definition and keys the number of cases. So they are very reasonably, the quality of the reanalysis is very good. We're able to produce heat waves. Next slide. Similarly, the cold waves also were able to produce. Next slide. Next slide. This cold waves also were producing. Next slide. And the precipitation, we found that the precipitation, our ANRs is one of the best compared to even ERA. Our precipitation qualities are much more better, and we are getting the analysis. And it is very, very well accepted, and many publications are coming showing these results. Next slide. Quickly. So this is the rainfall. Extreme rainfalls are well produced by Indian analysis that shows this one. This paper is published in that one. Next slide. I'll skip this one. Let's quickly go because of time. I'm skipping this seasonal forecast. So we are giving the seasonal extent forecast. And next. So in the future, we are going to scale modeling with 5 kilometer and 2 kilometer model was developed, and also we are going NWP from the atmospheric alone to coupled NWP, 10 kilometer coupled model was developed, and also what mentioned post-processing that with AML and other things for the post-processing techniques were developed. So this is our future strategy. Next slide. You can see that 6 kilometer model with expert convective scale, that down thing, the right hand has showed the satellite picture, and with expert convection scheme, we are able to simulate almost all the points that one. So the simulation quality, that 6 kilometer model is ready, and this operational quality is good, and so we are entering the scale model with the new computer. Next. And the other thing is, now we are going to use the, as I shown earlier, we have developed land data simulation in that one, and also NEMO ocean simulation system are there. And now coupled system at course resolution is there at 65 kilometers. And now we already tested for the last 2 seasons coupled and WP system. With this 10 kilometer resolution global, and with this one, and the system is almost ready. And next, these are the part of the weekly coupled data assimilation, where data assimilation is run at 6 hourly separately for what I mentioned, like the atmospheric data assimilation 4D, ENK 4D, or and ocean with 3D VAR and ENK for land data simulation then separately, and the couple to run the model. This one, this is such a weakly coupled system is in plus. As I shown in this JS 2023 and 24, we are tested this system very well. Next. So these are the parameters. Next. And for that one, ocean data processing system also is developed. All ocean observations are now we are processing the pre-process system all developed in that one. Next. Next. So as I told in the pre-processing thing, for a pre-processing we are developing a grand ensembles using NEPS and GEFS together. The grand ensemble was tested, and we are getting the best for. We are trying to get better, taking the limitations of the GEFS system and NEPS system. We are developing a grand ensemble system, and this recently we started sharing this grand ensemble for thing to IMD so that the forecast quality is improved. So next. So this is the schematic diagram of what we are doing. Next. And next, these are the improvements that we can show clearly demonstrate that EMOS using these systems with the improvements what we are getting were shown this year. Next. So, okay. And now we are working on the AI methods for the data assimilation as well as post-processing and the pre-processing where systems are being developed and people are working on that one. And we have shown the heat wave prediction and for the case of temperature and also near real-time rainfall retrieval from the radar and merging with the satellite data. We are using AML and this was demonstrated well with that system. Okay, next slide. So HRR, the DWR data we're using for the high resolution data file to get the nowcasting system capability. And as I told earlier, radar and also the DBNet data and high frequency data from the AWS which are coming within 15 minutes, all the data we are using for giving the nowcasting system and giving the things. Okay, with that, I think I will close here. Thank you.
Thank you. Thank you very much, sir, for this wonderful and elaborate talk. So we can have few questions. And so this AOLS is basically a LiDAR on board. So is it similar to that Calypso or?
No. This Calypso is for the course resolution, you have vertical profile to the harmonic regression. So it is a different.
And this observation impact of InSat 3D is very small. Whether how much data we are assimilating and compared to others, and why impact is not so prominent.
Actually, the InSat sensor, you know that the coarse resolution. Now we have the video set, and up to that side what we do the Japanese satellite and the Qualcomm, AMS satellite, all covering the region with the latest where we have very high resolution data sets are coming. So those satellites already we are using that one, and also the InSat navigation errors are also there in that. Not only that one, and with the latest improved high resolution sensors available, the impact is much more.
Sir, in that lightning product, so it looks like the blended product had the best performance. So what is this blending?
That was what you told the multi-physics things. So
Yeah.
we used two physical schemes, the PR92 and the scheme, weighted average. So that for this particular for Indian region, as I mentioned, as we are using the cloud top in one region, cloud top heights in that one. When monsoon period, we have the very low clouds and also top layer is single, so the cloud thickness is more. So that parameter, that scheme cannot work in the for Indian region. And similar PR90 as a scheme also not good. So with dense observations are available with the IATM observation network and also any post network observation of the using that thing, we computed the.
Yeah, it's not all.
So that way we are getting the better skill.
So any, yeah,
So,
Madhula?
I have a question. So this ensembles you are selecting, right? 18, 21 and all. So on which basis, how you select? I know the perturbation you do, but the number.
The number is selection of number is a tricky. Actually, it is depend upon our computational power also. How many numbers are required? The people we are that experiments are a course resolution. We did it, and if you go to 44 member, the things people are getting better things. But it is depend on the computation power available as well as to get the best forecast out of that one. So it is a trade-off.
Thank you.
Even that is
Always changes.
change.
Whatever the perturbation we need for today is not.
No. Number of members. Number of members are almost yes.
Always even.
Always.
Why?
No, actually, we are when we are computing this that weight things, we are plus and minus. So that the distribution will be simpler. In that way, we are doing.
Is it same in the physical perturbation also?
Yes, sir. Always we have to go with.
Physical perturbation it is not there, not like that. Physical perturbation because number of schemes are available, it is there. So we can do it is not like that.
The ensemble rule here in KF, they give a rule that always our perturbation should be 2 over n. It should be always equal.
No, that is for that for the initial condition. So physical thing that thing is not required.
So in physics also they give that, sir.
No, physics number of packages what is available is multi-model. Depend upon the schemes that is available and how much you things. 2n is that because of that things where we are generating the things. Here we are not generating.
No, sir. Here they are saying usually whatever how many experiments we do, it should be 2 over n plus 1 as the mean. So total we will have the odds.
Plus 1. Now plus 1 thing are going on. Because now you came at office, then they're not running the deterministic thing. Deterministic same resolution things everywhere implemented, and deterministic runs are not there. Ensemble run itself is giving the forecast, and the deterministic thing also a part of the ensemble.
Yes.
So right now we have released two kind of reanalysis data, that NGFS and IMDA. But IMDA has fine resolution and longer temporal period, but number of variables are limited. In NGFS, number of variables are large, but its temporal resolution is limited, means for a smaller period, as well as its spatial resolution is coarser. Means it is comparable to any global reanalysis.
Actually, NGFS we run to show the capability that we can design. Actually, when the ensemble runs are IMDA run is done, the plan and they're doing before they do that one. It is I am shown it. I want to show that we can do independently. I can plan my own analysis. So to show that one, this is not IMDA is a big monsoon mission project. This is a byproduct. I want to demonstrate that we can design and we can run the reanalysis. So the NGFS is a very, I think Dr. Johnny was there, myself and Johnny. We tried to demonstrate that we can design and we can run our own reanalysis. So what are the improvements that we done GFS system that I took and demonstrated it. And there is no budget or nothing is there for that. So
can it be extended?
No, we can do it if the computing power is there. No, that is variables can be generated because all the variables are All the things are generated with only the prognostic variables are fixed. Same in both the places. In IMDA also we can generate it. Here GFS also we can do it. But only thing is there is no system to do the GFS reanalysis. Only 2-3 people we did it.
I have one quick question. So in your FSOI plots, you showed, right, impact of observations. Why it is not updated after 2022?
It is. I showed that. It is 24 everywhere. It is there.
Last question. Sir, you made some experiments, local observation, right, to see the impact of such close winds with radio sonde. So for Rayleigh scattering. So in the cloudy means me scattering also any experiments done?
No, there was shown that B scattering upper level impact because that impact is more in higher level. Lower level also it is there. Lower level it is similar to radio sonde. In upper level more impact of the profile HOLS winds are more because at that time maybe our radio sends are not going that up to that height or the things. So B scattering is giving more.
Sir, in our GFS model, so there are biases we are seeing in the temperature. So this this may be due to the, I think, the main reason may be the LULC that we are using it. So most of the people know about it, but we are not updating it. So why we are not updating, sir?
That is the model development. No, he cannot answer that question. We can do it. You can do it.
We can do it. We can purchase data for LULC.
LULC data is available. We showed that NRSA locally is our Indian region only, but better LULC data. Here, what you are seeing that GFS is not because of the data, the change in the scheme. GFS, when we use GFS, the LULC source of the data is different. So that source may not occurring in that one. And GFS, the land data simulation system is missing here. So we needed to change the LULC. LULC almost same. The GLDAS system, if we implement the GLDAS system, I think we'll get the more implemented temperatures. Our temperatures mainly because there is no GLDAS system in our GFS system.
The 3DS data started to assimilate or not?
No. Products are not available. I think DG can.
Any online question? Online questions?
Online participants, if they have their question, they may please switch on their mic and they can ask.
In the chat box?
No, sir. In the chat box, we don't have any questions.
Fine. Okay, we can.
So let us thank Dr. V.S. Prasad for this nice and elaborate discussion and talk. And now it is time for us to express our gratitude to today's speakers, Dr. Rajesh and Dr. V.S. Prasad. I request our DGM to kindly felicitate Dr. Rajesh with presentation of a shawl and memento.
Yeah, I'll be ready with you. Thank you very much for it. Kiss me.
Now I request our DGM to felicitate Dr. V.S. Prasad by presenting a shawl and a memento.
Our privilege.
Today's program.
One more minute.
So it's an honor to present the vote of thanks, and on behalf of IMD, we thank today's speakers, Dr. Rajesh, with whom IMD and particularly EMRC works in close cooperation. And he is actually, you can say that our guide, our colleague, or whatever friend, whatever you can say, but he helps us a lot in developing the air quality early warning system, particularly the WARF-CAM and other air quality systems. We also thank Dr. V.S. Prasad. Of course, he is a part of our extended family. So, we thank him for sparing his valuable time and delivering this lecture and a wonderful discussion with the IMD and other participants. I also thank all my colleagues and specifically to Anup, who is helping us in managing these lecture series. Thanks to all the wonderful audience for interaction and listening patiently to the speakers. And our thanks to our Director General of Meteorology for guiding us, and under his guidance, actually, all these activities are taking place, and he is very much interested in continuing this particular series so that the young people can take the advantage of the senior experience of eminent scientists. And hopefully, I think this will continue for year long ahead also, after 15 January also, this kind of lectures. So thank you all for sparing time with us, and we look forward to see you again in next lecture by few more lectures are there with very eminent scientists from India and abroad. So keep looking at your emails on these lecture series. Thank you all. Thank you.